So now let's think about the homogeneous transformation. So we've already looked at translation to some extent. We imagine we've got a small translation that we're going to move something by, and we're going to represent this overall transformation then, which is going to be involving a translation, as being built up from two parts, ax plus delta, where delta is our fixed vector. Now A in this particular condition is just going to be the identity matrix, so it's not going to change x at all. But what we can do is we can say, well, we're going to add on a little bit, if you like, to the position, and what we end up with is adding on to each particular vector, in this case a component of t, which is tx, ty and tz. So this leads to a new position or a new vector where it's basically x plus tx, y plus ty, z plus tz. And like I said, this is an affine transformation. It's made up of two parts. It's made up of this multiplicative part here and also this addition part here as well. Now we can slightly extend that and actually think about, well, we've got the position now being shifted from one place to another using this translation and a linear map. But we can actually, instead of having the identity matrix in there, what we could do is we can put a rotation matrix in that part of calculation. And then doing that, we have the same structure, and what we do now is we first rotate and then displace the vector. Where in this particular case, as we see, we have a 3 by 3 rotation matrix. And also this rotation matrix and also this shift term in order to get the translation. So we can rotate a point using this transformation matrix, which implements a rotation. We can add on a vector in order to get a translation. However, this is, like I said, it's not a pure linear transformation. This is an affine transformation. So what would be nice is if we could actually come up with a way of making it much easier to handle rather than having two different operations. First of all, though, let's just bear in mind that if we do rotation and translation, we can't just change the order and get the same result. In this particular case, we start off with a plant pot and we rotate it and then we translate it. And that's not the same as first translating it and then rotating it. We notice implicit in the rotation here is the fact we're doing it around the origin of the frame, right? So this is rotating here around the origin. That's why it rotates around that point. And here we're rotating it around the origin. But now since it's moved a long way away, a rotation out around the origin gives you something completely different than we had when we did the other order. In a general case then, we often need to do rotation and translation. It's a two-step process if we do it like this. We've got to take into account basically the shift. So this is the shift P Borg and a rotation component. And we can represent that in this way. If we want to do that, that's fine. However, there are better ways of doing it, and what we'd really like to do is have just a single linear transformation which does rotation and translation. And we can do that if we do the following. Basically, we take our rotation matrix and we take our translation vector and then we append them in what's going to be a 4 by 4 matrix. Now, we first of all, at the bottom here underneath the rotation matrix, we have the first 3 elements in the row now 0, and the last one underneath the translation vector is a 1. What we also do is we also append our position vectors with a 1 as well. So we append a 1 onto the end of them. And this gives us what's known as the homogeneous transformation. And it's built up, like I said, of 3 by 3 rotation, 3 by 3 element rotation matrix, 3 by 1 position vector, and it's got these inclusions of these unity values at the end of the position vectors. So we can, in 2 dimensions, we can combine rotation and translation around quite easily, basically because what we want to do is, this is basically the equation we want it to end up generating. This is the two-dimensional version. Here we have the vector equation. X prime goes to the rotated x and y plus the translated value. If we actually multiply these out, right, let's do that, we can do that. We multiply these out, so it's x prime equals ax plus by plus tx, and y prime equals cx plus dy plus ty. We don't normally have to worry about doing this, it's just to show that we can now rewrite the system slightly differently. If we write it in this augmented form, like I was just saying, and in this case this is now a 2 by 2 matrix because it's in 2 dimensions. Now we've appended 2 zeros in the row underneath, and we've put a 1 underneath the position vector. We put a 1 underneath the position vector here. This is the offset, and we end up with 1 underneath the resulting position vector. If we expand this out, we'll see that we get the same result. Right, we'll see that x prime is still ax plus by plus tx, right? Because this value here multiplies against the 1. And then the second one, y prime equals cx plus dy plus ty, right? And the last row basically just gives us a 1. So what we've done is we've augmented our position vector, we've built together our homogeneous translation matrix, which is this part here, from the rotation component and the translation component. We've put in the appropriate values in the last row, and when we multiply this out, we can still get the x prime and the y prime. Obviously we end up with a 1 as well, but we just ignore that because we're not interested in that. So points are now represented, like I said, in this high dimensional space. xy goes to xy1. In fact, vectors would be represented by xy0. We don't have to worry about that though. So in the 3-dimensional case, let's do the 3-dimensional case because that's the one we're really interested in. And if you've done 3 dimensions, that's enough, right? We don't have to ever go into 4. We're not moving at the speed of light. So let's write this in the same format. Now we've got the rotation matrix part, or we got the rotation. This is actually obviously in this case it's actually an identity matrix. We've got the identity matrix here. We've got the translation that we want put on here at the end, and then we've basically put the end row in 0, 0, 0, 1, and we've concatenated a 1 onto the this position vector, and we've also done it on the other one. So if we had a homogeneous transformation for 3-dimensional rotation around the z-axis, first of all, what we would say is, yes, that this is going to be the 3 by 3 rotational matrix, right? So we know this is around the z-axis because the z-axis is points along the z-axis are unaffected. That's why there's a 1 here. All we have to do is just basically say, well, there's going to be no translation at the moment. We're not having any translation in there, but we're having the 0, 0, 0, 1 at the bottom here, right? So we've just basically just put in our 3 by 3 matrix here. We've put in a translation corresponding to 0, and we've filled in the last row. If we did the same for the x-axis, of course, then in this particular case, the x values stay the same, so the 1's up here. We've got our 3 by 3 rotation matrix for rotation around the x-axis. Again, we've got no translation, so that's 0, 0, 0, and again 0, 0, 0, 1. Right. And around the y, you basically put in the corresponding rotation matrix for rotation around the y axis, and that's what's gone in this section here. So that's putting them all together, x, y, and z. Normally you won't have to remember them. You should have them in information sheets if you ever get asked questions, because we don't want you to accidentally get something wrong for a silly reason like that. We can also combine the rotation and the translation together in the same matrix now, though, because now we've got this part, this translation vector part, that we can put in the translation that we're after, right? So in this case, what we're doing is we're rotating now around the x-axis, because this is the x-axis rotation matrix component. And now we're shifting by tx, ty, tz as well. We notice it first does the rotation and then it does the translation. And we can do the same for rotation around the y-axis and rotation around the z-axis. Again, in all cases now we do a rotation and then we do a translation afterwards. It's very easy to build these to implement these almost like in first principles yourself in Matlab. All I'm doing here is I'm just building the x rotation, rotation around x from first principles. I'm getting the cosine of theta, I'm getting the sine of theta. It's all in degrees, so I've got d's everywhere. That's just to let you know that's a d. And with this, in this case, we're just building together rotation matrix around x. Here we're building the one around y together. Here are building the one around z together. And yeah, we can basically do that quite easily in order to do some rotations if we want to do so. But we might want to actually build a homogeneous transformation, so that's very easy to do. So I've just showed you the rotations that we've had here. In this case, what we're doing is we're having a rotation around x. We're building the rotation matrix, so 3 by 3. In this case, we're going to say we're going to build a homogeneous matrix, but we don't want a translation in there. So what you say is you set the translation to be 0, 0, 0. And notice putting the semicolons after the zeros means it ends up as a column vector, right? So it's going to be a column vector. And concatenating things in Matlab is very easy. So if you remember, first of all, we want the 3 by 3 rotation matrix component, right? And then we concatenate. It's rows by column, so 3 by 1 translation part, right? And then we move to the last row, so we put a semicolon in, we move to the last row, and then we put in the 0, 0, 0, 1 that we need, right? So this is just built up from the two parts, from the rotation matrix and from the translation. It's just built up the homogeneous matrix for this rotation around the x-axis with no shift. And you can do the same for y. I'm just getting the y rotation matrix here. Again, zero translation, so it's just concatenating exactly the same way. Same thing you do for z as well. And we can easily build points up as well. So don't forget, when you're using homogeneous transformations, if you've got x, y, z as your vector for a point or the location of a frame, you need to add a 1 on the end, right? So you need to concatenate a 1 on the end. And it might be that you've got lots of points, right? This is what this is actually all doing. This is saying this could be a whole array of multiple points, and I'm just concatenating a 1 on the end of all of them. And of course, if we want to get the point back out again without the extra 1, you can just basically extract all the values except the last one, right, from the vector. And this is just building a homogeneous translation now with no rotation. So basically, you'd have, the nicer way to doing it would actually be, say, well, let's set R to equal the identity matrix and then do it like this. But what we're doing is we're just getting the T here and putting Tx in the first row, Ty at the end of the second row, and Tz at the end of the third. Okay, and so on, right? So now let's think about mapping points. We can use the same maths really to either translate points or map between frames, right? So what we can say is point 1 transformed by this translation or whatever it is, this transformation matrix gives us point 2. That's what we're saying there. So here we're going to basically being asked, the frame B is rotated with respect to frame A, right, by 30 degrees around the z-axis, and then translated by 4 units in the x, 3 in the y. Right, let's build this transformation. So what we need to do is to say translation, right? We know it's 4 in the x, right? 4 in the x, 3 in the y, so we put a 3 and 0 in the z. Notice I've written it without semicolons and I've stuck a transpose on it afterwards, so we end up with a column vector. And it's always very good practice to make sure that when you're doing these kind of things, the vectors you end up with are actually of the right form to fit in with the theory. Otherwise, you'll be sort of going through things by hand and flipping things up and down just to make sure they all work. Then what we do is we get a homogeneous transformation of this, and we could have done it by first principles and just put an identity matrix in and then put in concatenate this at the end and then put obviously the last row in. Then what we do is we're getting a homogeneous rotation of 30 degrees. So therefore the overall transformation matrix is going to be, we normally would then multiply a point by the first part, the rotation, and then we're going to do the translation. But because these are now homogeneous transformations, we can actually build the overall effect by first multiplying by the rotation homogeneous transformation and then multiplying by the translation one. Or we could have put the things straight in by hand, and this is what you'd end up with if you actually did that. As you can see, this is, you could jump straight to this and put in the rotation matrix part in this 3x3 part. You put in our translation vector in this part here, and then you put 0, 0, 0, 1 at the end. That'd be perfectly fine. If we want to do the inverse, well, one thing we could do, because everything in Matlab is a matrix, we could actually just calculate the inverse using the inverse formula.